Hello and welcome. A while back, I started studying large language models and neural networks, and there's a lot of videos out there, and at any point you end up in a lot of math, and the complexity scales pretty quickly. So I decided to build an analog neuron, a perceptron. And well, initially I found a paper from Frank Rosenblatt. This is from 1958. And the funny thing is that back then they already were debating three fundamental questions. How is the information sensed or detected by a biological system, and in what form is it stored or remembered, or how does that information influence its recognition and behavior? And a couple of years later, in 1960, the Bernard Widrow, who's a legend these days, built something called an ADALINE, an adaptive logic element, and it was literally an analog machine with a lot of dials and inputs and a small meter. And what this machine did was it emulates a single layer perceptron. So you have inputs, and then you have some weights, and there is a summation of all the weighted inputs. And then there is some kind of activation function. What are you going to do where is the threshold where you will say now the output has validity, or something like that. Anyway, I found another article just recently where this Bernard Widrow, actually this is from 2005, he describes how he built the ADALINE, and and basically what kind of significance this had for the discovery of this well-known LMS algorithm that many AIs are using today. And behold, there was a schematic of this ADALINE. And decided to try to build one myself, and I ended up with a schematic like this. So basically, see if you can see this in the camera. Yes, you can. So basically, plus minus 1.5 volt goes into a switch, and then onto a potentiometer. And then I've drawn all this like some sort of a bus. It's actually not. They're all just connected like a star in the same point. But you go from position 1 to position 16. With this exact same setup. So if you have 1.5 volt at some of the 16 inputs and minus 1.5 volt at some of the other inputs, well, by adjusting the weights, you can adjust which way the current runs in this kind of bus you have, and that current difference you get between these two lines is something that you can show on a small analog meter. And then of course there is a bias. There is a bias function as well, where you can adjust the balance between. So if this meter is not centered at 0 at the beginning, well, then you can make it centered. So basically, I built one of these. It's called a knobby ADALINE because it had a lot of knobs on the original learning machine or ADALINE they built. So yeah, I built my own. And you can see how that looks here. So we have 16 inputs arranged in a way where we can make simple patterns. And then there are 16 small potentiometers, trim pots, which will be able to use or adjust the weight or the amount of current that's allowed into this parallel bus. Structure, and then this calculation PCB over here basically sums it all up, and there is the bias adjustment as well, and you'll see a plus or minus deflection on the meter here. So let's try and power this on. Right now it's completely idle. I can adjust the bias and make it move if I want, as you can see here. But let's put it nicely and centered. Now we can train it, and let's start by training it to giving a positive reading for the letter T and a negative reading for the letter J. So we start out by building a T. So there we go. There's still nothing on the meter. The rule now is that I should increase the weight just a notch, positively just a notch for the ones I like, the ones which are now lit, and decrease the ones which aren't lit. So you can scroll fast through this process if you don't want to follow me, but I'm just increasing that a little notch. There's a small dial here. I doubt you can see it. There we go. And there, and there, and there. It's already getting a bit positive on the scale. And then I decrease all the other ones because I don't want them to have significance. So I go all through all those and I decrease them like that. And here we go. There, there, and there. So now I have a nice positive deflection of the meter. Then we can do a J. So let's set this to a J instead. Let's build a J. Here's a J. Now the unit is not trained, or my little analog perceptron isn't trained, so it will just display 0 for the J. But now the rules are the opposite. Now I need to decrease the ones that are lit up and increase the ones that aren't. So let's do that, meaning that this one will go back a notch, and this one will go back a notch, and that one will go back a notch, and that one will go back, and this, and that, and that. And then I should increase the other ones. Increase, increase, increase. And you can see what happens, that I end up getting a bit more negative deflection on the meter. Oops, that was wrong. Let's go over there and over there. So here we go. Now there are two ways you can do another T over here and another J over here as well. So let's just do that. Let's do the T. There's room for another T. There we go. So we want this positive as well. So the rule is I increase and I increase the ones I like. Increase. And here we go. Here we go. Oh, that's a bit too much. And here we go. And then I decrease the other ones. So as you can see, this is a completely without any kind of formulas, this demonstrating how the learning algorithm of a single neuron or perceptron is. So this one should go back as well, and back, and a bit back. And yeah, I already did this one, didn't I? So positive for the second T. Now let's do a J over here. Let's see. There we go. I hope you can all see this. Here's the J. We want this negative. This means that I decrease the ones that are lit, which is happening right now. So there and there. And increase the ones that aren't lit. There and there. This one comes always all the way over now. I'm running out of room. So, and that, and then we need this and that and that and that. So basically that's it. The training is done. Now I can return to my initial T. Let's see if that still works actually. So here we go. My initial T turns positive. Let's make that the other T, like that, positive as well. Then let's try the J, 1J. Let's make that happen like that. There we go, negative. And the other J, and you'll see that the amplitude isn't exactly the same for the different, but they go positive and negative. So in reality, this model, if you were to look at more than just not positive and negative, but the actual amplitudes, you'd be able to distinguish between these four 4 different patterns, which it is in a 4x4 matrix. Yeah, it's negative as well. So there you have it. It's an analog perceptron or an analog neuron. There are billions of those in language models, and we just trained it to be able to distinguish between T's and J's. The funny thing is, if you look at this, how these weighting coefficients now. How do I look? If there's small lines here, so this is at position 2, and that one is all the way over at 4, 2, and 0. This should be kind of 0 actually. So there we go. And 0, 2, 0, minus 2, minus 2, 0, 0, minus 2, minus 2, minus 2, minus 2, minus 2. So if you look at these in that same grid, this is how the my little perceptron, my little neuron sees the world based on what I just trained it to. And the funny thing is that these coefficients doesn't really in any way look like anything I trained it for. It's not like you can see, oh, there should be a T there, or there should be a J there. Some of them are even 0, which means they have no influence at all. So they're invalid. They're not unused. And this is a funny thing. You can't always by looking at the weights make out how this thing was actually, or what it was actually trained for. And from what I hear, it's something that's for the big language models that we're using these days. There are people doing research in this area. Where is the information actually stored, and how does it get there? What does it mean when one of those cells actually turn high? Is that a special term? Is that a special thing that the language model now looks for, and so forth? So, but I just wanted to demonstrate that even after training such a simple system like this, it's not logical in any immediate way why these coefficients end up where they end up. You can probably prove it by math, of course, but I promise you no formulas. But in here, just by logic, looking at them, you can't really see that they should end up the place they are. Okay. Anyway, this was a short video on the ADALINE. I built my own ADALINE, the analog perceptron. Hope you enjoyed this. I haven't really seen many videos about analog perceptrons out there. I think there's one. I noticed one, but I haven't really seen too many other videos about this concept. So maybe this can bring some clarity onto how neurons and by the end of the day, AIs they work. So have a nice day, all of you.